about functional programming in Kotlin today. I'm Rahul Dominic, and I'm a computer science student at the University of Waterloo. I'm currently in my 3B term. And I originally got into functional programming in my very first computer science class. So at Waterloo, our first intro to computer science class is actually taught in a language called meetup, which is a derivative of Scheme, which is a descendant of Lisp. So I was really impressed by the elegance and the minimalism of the code that you can write, given the basic functional language principles. But when I went to my first co-op job, where I was writing Android code in Kotlin, my mentor was super into the programming in functional styles and using a lot of functional principles. And that's when I truly understood the value of writing functional code, especially in a production environment. So today, I kind of want to go over some of the principles of functional programming. Why does functional programming matter? And how do these principles translate into concrete concepts that you can use on a day-to-day basis to just code better and write better code? Functional programming, unlike imperative programming, where imperative programming is based on writing a whole bunch of statements that alter some sort of program state. Functional programming models programming in terms of computation with pure functions. And what are pure functions, right? So functional programming in itself, just the goal is to make things easier to read. Its whole goal is to make it easier for programmers to reason about the code that they're writing, and to make it more understandable and less cognitive load. So, I just spoke about functional programming is based around pure functions that model computation in given a few certain set of rules. If we talk about pure functions, the properties can be broken down to roughly three categories. One is pure functions are total, they're deterministic, and they're incalculable. These three words probably sound like not much, so let's actually step into these and figure out what they mean. Total functions are functions that return a value for every input. This might seem like a very simplistic property, but let's actually think about what this means. When a function returns a value for every single input, you can say a couple of things about that function. It means that given a set of inputs of a certain type, you will always get an output of a certain type. That means that it doesn't throw an error, it doesn't print something to the screen, it doesn't do anything that is not return a valid output. And when you think about it, that makes it super easy or less puts less stress on the validation of inputs and outputs. You need to care less about what these inputs and outputs are, and all in all, it leads to less undefined behavior. Right? The second thing is deterministic. And what deterministic means is that it always returns the same output for a given input. If you call a function 100 times given the same input, it will always return the same output. And again, what benefits does this give a developer? Well, if the function is an expensive computation, if it's a network call that rarely changes, then you can add caching to it, right? If it's something that guarantees to be the same value, there's no point in calculating it again and again. You simply cache the value. And deterministic functions are inherently easier to test. They're easier to test because the tests are less flaky, and you kind of know the domain of the function's outputs. And when you have better tests for a function, it means that refactoring the code becomes super simple. That means if you replace that one function with something else, and the tests pass, you're pretty much sure that it's going to work in a production environment. the last one that we were talking about was inculpable. This is just a fancy way of saying that there's no direct interaction of the function with the outside world. But what does outside world mean? To a function, the outside world is anything that's not in the signature, that's in the parameter list return type, and in its body. Anything outside of that is the outside of the world. That means no mutation, no sharing global state. It means not accessing or printing anything to the screen. And again, what does this really mean to functions? It means that what a function does, you can see in its signature. If a function takes in a certain value and gives out a certain value, you can be sure that that's all it does. And another, yeah.
So question about that. Does that mean that dependency injection is not a functional, or is it like a bad pattern?
I wouldn't really say that you could do a dependency injection with pure functional programming, like you can. It's just that it takes a little bit of work to get it to be purely functional. And again, this doesn't mean that effects are not possible, like printing to the screen or dependency injection or network calls. And we'll get to that a little later in the hour. Yeah. So getting back to this, when a function doesn't share any global state, it means that it can be infinitely parallelized, because forget about two functions changing something on its own thread. If it can't change shared memory on a single thread, it definitely is safe to do so on multiple threads. And that's kind of the power that this gives you. And then again, the question that always comes up is, why does this matter? Our programming languages give us so much ability to do so many things efficiently. Why do we want to restrict ourselves to these constructs, right? And one of the best lines I've heard is, restrictions liberate. What does this mean? We put so many restrictions on what a function can do that inherently we know what it can't do. We know the things that we don't need to test about. We know the things that we don't need to think about when we're developing. And that reduces the number of things the code can actually do. Think of this as like a menu, right? The number of things your function can do is the number of items on the menu. The lesser there are, the easier it is for you to pick your dinner. And that's kind of the same concept here. It makes things easier to reason about, it makes your code easier to understand. But let's jump right into some real code. Right? When we talk about function programming, the very first thing that most people think of is functions as first-class values. What is this? Why should I care about it? And what benefits does it really give me? Let's say I want to write this really simple function. It generates it gives me the even squares of numbers from 0 to some bounded value, right? And this is kind of what you'd expect from an imperative piece of code. It's a for loop that squares a number, checks if the number is divisible by 2, appends it to a list, and then at the end returns the whole list, right? Pretty simple. And I wouldn't say this is too difficult to understand. What if we're writing another function now? The odd cubes. It does the same thing, except it returns a list of the odd cubes of numbers from 0 to 100. And what are we really changing from these two functions? It's just those two lines of code up there. Seems a real shame that we have to rewrite such a large function just for 2 lines of code. So what can we do to abstract this away? We can start by moving that power into as a parameter, right? Then we have a function odd power, where we can generate something called odd cube by passing in by calling it as a subroutine and passing in 3 as a parameter. This is a little better. But what we really need to abstract away is that odd and even concept there. That's when we can actually reuse it between the two functions. But let's stop there and think, is this really what we want to do? Do we just want to abstract away the odd and even concept, or is it that we want to abstract away that whole condition? We want to be able to use something like this for any function. We don't want to be able to use it just for odd and even cases. So what we really want is something like this. We want the odd cubes function to generate the list. We go over each element in the list and transform it by cubing it. And then we only want to keep the odd elements. That's basically what we want to do. We want to first transform every element, and then we want to decide whether we want to keep an element or not. And these actually are functions in Kotlin, and they're called map filter. We'll look at what these functions are, but in general, what are these category of functions that take other functions as parameters? They're called higher order functions. And higher order functions are a direct consequence of having functions as first class values. It means that having functions as first class values, you can assign functions to variables, you can pass them to functions, you can even return them from functions. So what are these higher order functions? The map function we just looked at right now, it takes an anonymous function or a lambda as a parameter, and for every element in that list, it applies this function and then returns a new list. This is a higher order function. But you can also do something like this, where you have a function, in this case adder, which takes in a value and generates another function which can be applied to a value to add this to. So for example, we can say adder of 1, which generates a function called add1, which you can use to add 1 to any other number. And this is another example of a higher order function. And what we see is higher order functions abstract away repeated patterns in our functions. It's a way to abstract code just as classes do for data, right? But it's actually so much more than this. In our case, the higher order functions abstracted away control flow, but higher order functions do something even greater. They make functions composable. Just like you have classes that abstract away data and their related methods, you have function composition, higher order functions, abstracting away lines of code, so repeated patterns in your functions. And just like inheritance can extend the ability of classes, your abstractions for data, higher order functions extend the ability of methods and functions and make them more reusable. This is just another thing in your toolkit to make code reuse possible. But let's step into a real world example. When would you really use something like this in real life, apart from simple maps and filters? Let's look at networking. So throughout this talk, we're going to be walking through a couple of examples that basically build an Instagram app. So in this case, we want to get the user's information, the user's profile information. So we have this method that uses the Kotlin Fuel library to make a request to get a user's profile. The network is not always reliable, so we want to kind of retry a bunch of times to make sure that the function failed for reasons that it should fail for, and not something flaky like network latency or intermittent switching from 4G to Wi-Fi. So what we would naively try to do is, in a for loop, we would wrap our network function in a try-catch block, and if it fails, just try again. Otherwise, break from the for loop. And this works pretty well. So assume you're happy with this, and now you want to apply it to a whole bunch of other functions, right? And then you get something like this. You want to get all of the followers for a user. So now you get the user, and then you make a request that could fail. So you want to wrap that in a try block with a for loop. And then you get the follower IDs. And then for each one of those followers, you want to get the full user object. So then you need to make another call to the getUser function to get each one of these users. And this leads to this whole mess of code that no one 5 days later can figure out. So what if you could abstract that whole bunch of for loops and try blocks into a higher order function? Because all you really need to do is retry a block of code, see if it fails, and if it fails, give it another shot. That's all you really need to do. So we can write a function called retry that takes in a code block and the number of times you want to retry it. And what it would do is literally the same lines of code. If when we execute the block, there's an exception thrown, you catch it and you continue till we're out of times to try. And that's pretty much it. And you've got a piece of code. Now let's see what this looks like. Now this looks much better because we don't have a whole nesting of for loops and try blocks, and all we really have is retry 3 times, try this network request, and then for every object in followers, retry 3 times to get the full user object. And now if someone looks at this piece of code, it's a lot more easier to understand. It's a lot easier to understand what exactly this piece of code is doing. We can make this better. Using higher order functions, we don't need to have this for loop running there. We can instead turn that into a map. And then for each one of those elements in the follower ID, we can make the API call, retry within that, and then once all of the followers have been processed, we can then do whatever we need to do after. And this looks a lot simpler. This code, in a sense, turned like a whole bunch of spaghetti code into something that is not just cleaner, but it's also easier to understand because we're not dealing with random for loops and try blocks. We're dealing with something called retry. We know exactly what it's doing. And that's kind of the power of higher order functions. So let's step into something else that is super common when people talk about functional programming, and that's immutability. So Kotlin in itself is big on immutability, being influenced by functional programming. But why exactly does immutability matter to functional programming? It seems sort of disconnected. Well, immutability isn't so much immutability, but it's the lack of immutability that means that we can't really guarantee some of the things that we would normally do about pure functions. Let's take a look. Deterministic. Returns the same value for every input. How can we really guarantee that a function is deterministic if it depends on things that are not in its signature, that it doesn't take as an input? Let's look at this. We have a simple function that calculates the area of a circle, and it uses a mutable value pi, right? So this works just fine, everyone's happy, it calculates the right value of pi. Then what if someone writes a really evil function that seeks to change the value of pi to 3? This doesn't look good. So what if you call area of a circle on the value 7? You call this function and then you call area again. With the exact same input, you get 2 different outputs. That directly violates the deterministic property. And another very trivial thing that it violates is incalculability. By its nature, we're accessing and mutating global state. The function isn't supposed to know anything about pi, yet we're using its value. And hence, this is inherently violating the properties of a pure function. So, immutability is bad. Mutability is bad. let's take a look at real world example about why this matters. So let's move slightly down the network stack, and we want to get this value of the user profile and the posts that are related to this user profile into a view model, right? So let's take the example of the user refreshes his page, right? So you want to refetch the user profile, you want to refetch the posts, and you want to do them at the same time to make sure they're efficient. And this is totally something that could come up in real life. Let's take the example of Kotlin Waterloo. So we have this refresh user data function, and it spins up two threads, two background threads, one to get the user and one to get the posts, and set them in the view model. Who can see a problem with this? It's in these lines right here.
There's some repetition.
Well, it's actually a lot worse than that. Those two lines there modify the same part of data, the same part of data. And what does that mean? It means that this can lead to inconsistent state. So let's say that the first background thread is running, and then just when it's about to copy its data into the view model, the second thread runs and decides to copy it in first. And now you have a race condition there where the post thread thinks that it copied its data into the view model, but then the user thread overwrites that data. So now you have a race condition there about which data gets in first. So
Just a quick question. What's the suspend keyword do?
Suspend basically just means that, well, it's a Kotlin coroutine function that can basically be run asynchronously. It's just it's a modifier that Kotlin provides for coroutines.
So I'm not quite clear on what it does.
It means that it's suspendable, so at some point it might do something, and then it might make like an IO call, and then it's just sitting, waiting, not doing anything useful. So in that point, that suspended state, coroutines can like put that aside and do some real work, flip it over. And when the data comes back, it can continue that. So it enables that ability to put things in and out of what gets executed.
Okay. Thanks.
Yeah. To this example, the suspend keyword doesn't really impact the code. Yeah. So it's kind of that you have two background threads that are modifying the same block of data, and coroutines knows that this is the source of problems. So they have something called mutex, right? So mutex is just short for mutual exclusion, and what that means is that it locks out that bit of memory and only allows one thread to actually change the value in that block at any point in time. So this works. So this would ensure that that memory doesn't modify, that memory isn't modified by any other thread if one thread wants to write to it. But what's the downside? It kind of means that now you're forced to, wherever you have this view model being modified on any thread, you're forced to kind of wrap this around in the mutex because you're not sure if another thread is going to modify it while you're using it. And that's really not the nicest solution. Another thing that you could possibly do is instead of having the setting of the view model done within the thread, you can await the result from both of these asynchronous calls, and then you can set the view model all at once altogether. This works. This is correct. However, it really can't guarantee that no other function is spinning up another background thread that's going to modify that view model. So your view model is So this function still cannot be certain to produce the right value. The only way we can really be certain is by passing in viewModel as a parameter instead of having it as a global object. And the reason for that is that since it's a local local variable parameter in this case, you're sure that the copy that you have is the only copy that you're going to modify. And when you return it, you don't care basically if something uses it or not. But from your point of view, that's all that matters. Yeah.
But that would require that you only passed as value into the function, and then when you copy, it's actually putting it in the model, and not maintaining the existing one, right?
Correct.
Wouldn't that get costly?
So, yes and no. Copy, like smart people have figured out a way to really copy these objects like lists and objects like this to be less expensive than if you would copy every single field. For example, if you just change one field, then you can pretty much maintain the reference to each one of the other each one of the other data attributes, and just change this one right there. However,
yeah, I understand that. Like, okay, you might be talking about data sharing.
Yeah.
But like, what I mean is like, what attributes does the view model need to have to even have that thing be possible? Like, I can't take any class view model and just expect it to work, right? Like, it has to have like a special kind of class.
well, so you're saying that you need to have a special class that implements these efficient ways of copying to get the benefits of it? I'm not quite clear on what exactly you're talking about.
Yeah, like so like what I'm basically saying is like if I were to make a view model class which doesn't have anything else, and it doesn't have my variable properties like use and posts on it.
Yeah.
And if I were to pass it down, will it automatically go where like copy by value by like data sharing, or will I have to inject a piece of code, tell the view model like no, like this is how you like handle it?
So I'm pretty sure, although I'm not 100% sure, that it does implement these optimizations to make it easier to copy and replicate data. However, one thing that I do have an answer for is that although yes, definitely this is more expensive than actually mutating data, you kind of pay for that higher level of abstraction. You kind of pay for that safety that you get from having immutable types. Just like having a class is more expensive than having just a whole bunch of variables, you pay for that. You pay for that efficiency, and it's exactly the same thing with having immutability. You pay for the security in terms of reducing performance. So yes, it does reduce the performance, but people have found ways to make it not as bad as it could be.
And to answer that one, like, do you have to personally address the class to make it efficient? Yes. It's not automatic.
But if you do cloning on lists and stuff like that, Kotlin does. I'm pretty sure that Kotlin does provide optimizations to make the cloning process efficient.
Question.
Yeah.
If you're passing view model to a method, it just copies the reference, right? But it creates a reference to the same object, the same memory location.
Well, yes, you're copying the view model here, so you're ensuring not to modify the data here. You're returning a copy of the view model.
So when you call the two things, like one to fetch user, one to fetch the other thing, I'm assuming you're making a copy of the view model and giving each one of them copies for each of the asynchronous calls.
User and posts.
Yeah.
So the idea, well, that's implementation dependent, but ideally those wouldn't really depend on the view model, because you're passing in the data it needs to make the network request and return back its results, and then you update the view model. So it's kind of separating the concerns between networking and updation of the view model.
So when one of them makes its own copy of the user, one of them makes another copy for the post, and you get back two view models, and you have to somehow merge them together.
I'm not sure what you mean. Are you talking about these two calls here, get user and get posts?
So for so get user will, after it gets the user, makes a copy of the view model and sets the user details on it, right?
Oh, so no. If we look at the previous code here, we had within launch, we had get user being called and then the view model being set. But over here, outside of async, we're actually setting the view model. So we just get the user value and then we update the view model.
Okay.
Yeah. So yeah, we can work around some of the problems by moving things outside, and yeah, we can work around some of the problems by moving things outside, awaiting the results for both the users and the posts, and then updating the view model. Or the only way that we can ensure that the view model is up to date is by making it part of the parameter list. That way, we're ensuring no mutation. And yeah.
So what does the run blocking do there? It ensures that only one of these threads are running at one time.
So the particulars of coroutines, I'm actually not very familiar about. I use Navik's Java a lot, but
I guess I'm just wondering, how is this better than just creating a copy every time? I mean, you mentioned that if we synchronize every block, then if you have a mutex, if you acquire a mutex every time, then that kind of forces you to be synchronous.
So yeah, run blocking.
Just do that too.
That's exactly what it does. Run blocking means it's not an asynchronous call, it's a synchronous call. We're going to wait until this completes before we return to the call.
So how is this going?
The question that you have is actually different from this. Having a mutex there is not really, like having a mutex works. There's no real problem with having a mutex. The problem just arises from the fact that wherever you have your view model being updated, especially if this was truly asynchronous, you would need to wrap every site where you modify your view model with a mutex. Because now every single time you mutate your view model, you run the risk of another thread overriding that data. Basically, you have what's the word? Yeah, you have race conditions. Yeah, I don't know why I forgot that. I just finished a class on this, but yeah, so you have race conditions with that. So yeah, that's the only.
And then using it inside of a function allows you to not have to do that every time. Is that the advantage?
So when you move to this, you wait for both results and then you set the view model outside. It makes it so that those two threads up there, the ones that you spin up to make the two requests, those two don't really interfere with each other. There is no race condition between those two threads. But this doesn't guarantee that there's no race condition between any other threads that you spin up outside of this function. Does that sort of make sense? Okay. So, yeah, as I was saying, the only way that you can basically be sure that there are no race conditions is by removing the mutability factor of this. And as I was mentioning, immutability is costly. You do have to make copies. But just as every single level of abstraction that you add, you make trade-offs between the amount of space that you need, the amount of time complexity you're adding, and you make that trade-off for aspects like safety or for parallelization. I would argue that the amount of time that you would spend in the cloning process, you could actually save by parallelizing functions that you wouldn't normally be able to parallelize because of immutability. And it's kind of what a lot of Haskell users talk about. So let's actually step into this get users function and see what it actually does. Right? So get users, it makes a simple network request right here. If everything goes right, if the network gods are happy with you, then you get a good response. You have your user object there. But what if things don't go well? What if by accident you write in an invalid user ID instead of using the one from the previous request? Highly unlikely, but it could happen. This would throw a request this would throw an error every single time. So you want to handle these errors. So you want to wrap this in a try catch block, and then you'd be able to handle the errors in a graceful way. But what's the problem with this? The problem was 5 seconds ago on the previous slide, there was nothing that stopped me from not wrapping this in a try catch block. There was nothing that said in the type system that said that, hey, this throws an error, you should probably care about that. And that's kind of the problem. When you throw an error, it's not part of the type system. So you really can't be sure that your code is error-free. So what might we do? We kind of have two cases here. We have a case where you're handling successful data, the user object, everything's good. And then you have a failure case right there where things aren't good and you get an error state. So how do we want to model this? What if we have a class called result, and then we have two types. We have a success type, which holds the value that we really want. In this case, it's type T, or a failure class, where in the worst case, if something fails, it wraps an exception. Now this would work. All we really need now is a way to actually get to wrap data in these objects. Because if we have to use the constructors, well, we're going to be stuck with the same try-catch code, and that's really not going to help anyone. So we add a function in the companion object from. It basically takes a block of code, it's a higher order function, takes a block of code, and it runs it. If it executes correctly and returns a type T, we wrap it in a success object. That's exactly what we want. But if it fails, we wrap the exception that it gets us in a failure object. And that's pretty much it. Let's see what this does. Now, instead of our get user and get follower IDs returning just the values, it returns a result. So now, in the signature itself, we know that this can fail. We know that this wraps something that we need to use, that we need to unwrap. It has cases that we need to handle. But wait, how exactly do we unwrap it? We need to use user to get our followers, but how exactly do we do this when it's wrapped inside a result? So we need something to get that out, to get that data. And the naive way of implementing this would be to write a function, or to write a method called get or else, which in the success case returns the true value that we want, but in the failure gets some default value that we return. And that's what we do. Let's see what happens. We want to get the user object from it, so we use get or else. But what else? What is that default value that we really want to supply it? No default value here really makes sense. We're either forced to create some empty object, or we're forced to make this nullable to return a null, but that really doesn't preserve the failure aspect of it. If we step back for a second, we really don't want to unwrap that. User is just an intermediate step in the sequence to get followers, right? It's just this intermediate value that we kind of have to deal with that can fail, but it's something that we need to deal with to get followers. So instead we somehow want to chain this result to get to get the followers from that object. So we might be inclined to write something like this. We have a chain function which takes in some sort of mapping function. If the result object that we're talking about is successful, then we want to be able to map that data to something else. So we want to call it on that function. But if it's a failure, we don't really want to lose this failure data, so we just propagate the failure. And that's kind of what we have. So let's see what this would get us. Now this looks a lot better. We have get user, and now we use our chain function to unwrap the user object and then make a second network call to get all of the followers. Now this is so much better than the code we just had. But what is this result object and what is this chain that we've written? In functional programming, this type of result object is called a monad. And what really is a monad? It's just informally, you can say that a monad is any object or any abstraction that has a constructor to wrap values with and a chain operation, which is normally called flat map. But again, this is very abstract. What really does it mean, right? A monad is just a way for sequencing computations. So just as in the previous example, we sequenced a bunch of computations together in the context of error handling, we can do the same with a whole bunch of other contexts. So if we look here, our first sequence of events was that we wanted to get a user. But now that user could possibly fail. So we want to handle that error. So our context becomes error handling. But the user is just a single step in a sequence of events to actually get followers, right? So what we want to do is, in the next sequence, is use our get followers call to get the followers and return that result. In that sense, it is sequencing a bunch of these functions together to compute followers while abstracting away the context of error handling from our code. And this can be applied to a whole bunch of different types. The whole concept of monads at this point probably sounds super vague and abstract and really nothing solid to really grasp on, but it's intentional. The definition of a monad is so broad that you've probably worked with monads before if you've ever worked with lists. A list is a monad. There's a way to wrap data with a list, and there's a way to flat map that data, the data contained within a list. So you could say that monads are abstractions over not just control flow like we just spoke about with results. They can be abstractions over data, over other control flow stuff like futures, which is sort of like a JavaScript promise, and side effects like I/O, which we'll get into in a minute. So all of these, so monads just allow us a uniform interface over a whole bunch of different situations where it abstracts over domain-specific code while allowing you to generally wrap information with it and sequence computations on that data. So the best way to think of this is to just get into another example. So let's step back into our previous example with refresh user data. And we have these two calls. We never really handled what would happen in an error case, and nothing would. So let's look at how we handle it. We get users and posts to return results. So right now, we have them return result values that we would then use to compute the view model just as before. So we take the user result, and that's really we choose that to be the first step in our sequence of events. So we want to unwrap that result. So we want to get the user object that's within it. And then we want to also unwrap the post results. So we map over that result, get the post's data, and then we create a new view model from it. And flat map then you basically flat map result returns a result that wraps a view model. And then finally, in this case, like we pretty much just swallow the error if there is one, and just return the old view model. But in real life, we really wouldn't do this. So yeah, what do? We kind of composed the two results that we got together, handling both of their error cases, and only in the case when both of them are successful, we create a view model and then we return it. If either one of these steps fail, it short circuits and returns a failure. So we have encoded error handling directly into our type system and can compose them together. This code is still super messy and a little bit hard to follow. So in reality, we can actually combine the flat map and the map together into a function called combine. So what we do is, this is supposed to be post results here. So sorry for the typo. But yeah, so we would combine the user results together with the post results, and that would generate a pair of unwrapped user and posts. So combine would handle the case where if one of them fails, short circuit to a failure. If both of them fails, short circuit to a failure. Only in the case where both of them are successful, unwrap the data and then build a view model with it. And finally, to actually get the view model, you need to handle that error case. You need to handle what happens there. And that makes this networking, this function, mostly deterministic and total. So that's basically the power of Monads. It gives you the ability to abstract over a specific domain and write a sequence of computations very separate from the domain that you're actually handling. So now we no longer have a bunch of nested try blocks. We have something called a result. We don't have random exceptions being thrown and we don't know about it. We have in our type system something called result that we have to unwrap. And all in all, it just makes our code so much easier to understand.
Yeah, still have a get out of this thing.
Yes.
So I mean, I understand, but you probably still will return a default which.
I'm not saying that that it's never the case to have a get or else. Get or else definitely is part of a result types methods. It's just that in that intermediate case where we weren't ready to return a final value, where we weren't ready to return an unwrapped type, we just wanted intermediate computations. And in that case, we didn't need to use get or else because we'd lose a whole bunch of data and we really shouldn't unwrap it at that point. So it does have its place, and there are actually better methods to handle this, but for simplicity's sake.
And my next question is, anyone who tries to handle this will not be total, right?
Will not be?
Won't be total, because you would have to fail at some point.
That's not true. So think of it this way, right? If you have a function, like right at the top, if your main function for your program catches every single error, your program will be total, right? Trivially, it would be total. In this case, your result catches all the network errors. Assuming that's the only error that can happen in this function, when you want to handle it, you need to specify a failure case. So in a sense, yes, your network request failed, but your program didn't, because it just chose an alternative code path to handle that failure. So technically, you're still total.
But it may not return. I guess I see what you're saying.
Yeah. This always does return a value, whether it's a failure result or a success result. Yeah.
How easy is it to step through the debugger?
So not too bad, because assuming you're using data classes, which you really should be, you'd get the object that you have within the result on the debugger print logs, right? So you shouldn't really be too bad with the debugger.
So what do you say to the object-oriented community that says object orientation is easy to model the world, yeah? You have the objects and members and so on. So how you, for example, how you do inheritance of polymorphism in a functional way?
So polymorphism is still super possible with functions. It just takes a little bit of a different style. And it's not to say that object-oriented programming doesn't fit in with functional programming. We still have the need for classes. We still have the need for data abstractions. It's just that we're adding the ability to have function abstractions. We're reducing the number of things that your function can do. It doesn't mean that object-oriented programming is incorrect. It just means that you kind of modify it a bit. And I would kind of say, rather than this competing with object-oriented programming, I would say that it's more on the lines of competing with imperative style, where you do have statements that modify some state. So I would say there's definitely room for both, and in a lot of cases, well, not a lot, in some cases, it totally makes more sense to go with imperative programming over functional programming. For example, if you're Google and you want to write some super efficient piece of code on your data center, you probably want that 5 milliseconds of efficiency map, right? In that case, don't go with functional programming. But if you're something like, I actually do know that Duolingo uses Scala. So Duolingo uses Scala for one of its microservices that basically serves its lesson content. And that's a system that needs high reliability. And in that kind of a system where you have the ability to cache results, and efficiency isn't really the biggest piece of importance there, go with functional programming because reliability matters more. So it's kind of a mix of the two, and it's domain specific. And that kind of ties back to this statement, right? Functional programming makes it easier to reason about your code. We kind of, over the last hour, we walked through the various, what really functional programming is. It's made of pure functions. What is a pure function? What are the properties of a pure function? And how do those properties manifest itself in real code, right? How do you make your code purely functional? And what are some of the techniques? And as you can see, with higher order functions, with monads, with immutability, the result was always the same, in that your code was easier to reason about. Not just was it cleaner, it was also better named. Things were better representative. Your code was more declarative. And I believe that is kind of the most important takeaway of functional programming. Now that's not to say that tomorrow you get into work and you decree that every piece of code needs to be functional. You can start getting the benefits of functional programming just by doing a couple of things. For example, by using immutable types, by using some higher order functions like map and filter instead of iterating. That itself adds a whole bunch of clarity to the code that you're writing, and it adds a bunch of reliability. There itself you can see some of the benefits, but I think the biggest benefit to start with that I felt is using the result tag. It does make error handling so much easier, and it's stuff that you can see. You can see your error rate falling. You can see in code review. It makes it so much easier to say that, hey, this throws, you need to handle this, and it makes things a lot easier to think about. It reduces the cognitive load on developers, and all in all, it just makes your life easier. Kotlin out of the box has a whole bunch of functional programming abilities, pretty much because Kotlin was heavily inspired by functional programming. As we saw, Kotlin supports first-class functions right out of the box. It has immutable data structures like lists, sets, and maps, some of which you even need to explicitly specify that you want a mutable type to get. And also it has read-only types using val. you can create classes which have only val fields to ensure that someone else isn't modifying the data that you're using, the data that your class holds, that your object holds, and it's only modifying the data through methods that you yourself have approved. And all in all, it just makes things easier. And this itself gets you quite a bit there. With this itself, you can see a good bunch of reliability jumps. But there's a whole bunch that Kotlin doesn't natively provide. And that's where the Kotlin community has stepped in with Arrow KT, which is a functional companion to Kotlin's standard library. And what that means is that Arrow just has a whole bunch of abstractions on top of Kotlin, on top of the standard library that it provides, to write more purely functional code. For example, the result type that we're talking about is try right there. So it has a result type inbuilt. And something that we didn't talk about that I think is worth mentioning is the IO type. Secretly, the function that the networking function that we were writing this whole time, although we tried to make it as total, as deterministic, as inculpable as possible, is not purely functional. Because it's not deterministic, it depends on a server result. And that server result simply means that you can't guarantee anything about the function. Well, the IO monad of Kotlin, of Arrow, basically helps create effects like network calls, like reading from caches or printing to the screen. It helps write those effects in a purely functional way. And the reason it wasn't mentioned here is because that's a whole talk on its own. And it's pretty cool what you can do with all of this. So, pretty much, this is what I wanted to do with this whole talk is to kind of get you part of the way there, to tell you enough about functional programming and the values that it can have to your day-to-day life, to get you interested enough to start picking these things up and actually seeing what it's worth. This is nowhere close to an exhaustive list of all of the benefits or all of the techniques of functional programming. But I hope it did do its goal to get you interested and to kind of help you write better code. So, thank you for all your patience. Any questions? Yeah.
So, awesome presentation, thank you. I've been using the functional contracts that are built into the standard library, like the map and flat map and those things. Really awesome higher order functions. But I haven't really used like the higher level abstractions like Monads and stuff like that. Now, I've read about teams using Scala and they went like full blown into that, and then they got into a stage where like a lot of people had trouble understanding the code base. Is that because of Scala, or is that like some of the functional things taken too far?
I think it can be both, and I think it's kind of this whole spectrum of what you really want to do. So some parts of your code are worth more than the rest. They're the code that generates revenue, the things that break, that if they break, are going to mean you lose thousands of dollars, right? And it's that code that you kind of need to make sure is more reliable. While definitely there is a massive learning curve to actually learning how to program purely functional, the benefit also exists. So when people actually code in Scala, they are the people who really need that benefit of having fault tolerant system, of having high reliability, high parallelism, and so it is a trade-off. You do trade off some of the readability, and kind of everyone on the team needs to be familiar or needs to be okay with ramping up to that system, to that level of functional programming. So it's definitely not recommended for everyone and for every system. But I do think that there are some low-hanging fruit, especially with monads like the error handling using the try monad. Those are low-hanging fruit that is very easy to pick up and will give you great benefits. So it's kind of where each team needs to see how much of functional programming they really want to incorporate in their project, and kind of go from there. Like, like I absolutely love the result monad. I mean, Swift has. I think there are definitely things that you can get started with right now that have a less impact. And as the team scales up to understanding more functional concepts, it wouldn't hurt to start moving that level up. But yeah, it's very subjective. Anything else? Yep.
So for the result moment, I was wondering, does it ever inform the user that something failed has happened, or does it just silently pass you an alternative result?
So one thing that we've done in the past is so the result monads generally are generated like right in your network call. So for example, if a network request fails, right, you return result failure, and then it passes through your view model. So if you're using MVVM architecture, it passes through your view model, and then your view model sees, oh, it's a failure. Let me call or let me trigger the error dialog or something like that. Let me do something to detect as an error. Or what I've done before is I've mostly used results with RxJava, because then it really matters for you to handle your errors. The result monad goes all the way, passes through the view model, and hits the subscription point for the view model at in the fragment or in your view, whatever, depends on what you're developing, and right there you handle it. So you handle it saying, oh, let me unwrap this. So we have a function called match, and that kind of is derived from Rust. So let's see, is this a success? If this is a success, great, let's use this data. But if it's a failure, oh, we have an exception. Let's see what the message is. Okay, this is a network failure. Let me show a dialog to the user appropriate for this failure. And that's kind of how we handle it, right? So you can do a bunch of things. Either handle the result intermediately, like unwrap the value if you're certain that that's when you're going to need it. And that's what I did a couple of times when we had an MVP architecture. Or you could just send that all the way to the front, all the way to the view, where the user knows how to handle it. So it's a bit of both.
So I'm more asking, for your example, it seems like you silently not handle it. So I don't know if that's what you're
Oh, definitely not. Like, do not swallow errors. Like, the only reason I did that there is because I was running out of screen space.
Yeah.
So it's not a good idea to do that at all. But in this case, for the demo purposes, I decided to, it's not a good thing. Anything else? Okay. Cool. Thank you.